Hello, it's Austin Meyer, the X-Plane guy, and today we are going to talk about the new jet engine thrust model in X-Plane 12. So it used to be in X-Plane I would curve fit the jet engine thrust to match what actual jet engines do. But I've been doing some more research and I've now been able to get rid of these curve fits and actually boil the thrust down to simple first principles physics rules. So X-Plane actually now predicts jet engine thrust based on first principles rules rather than just blind curve fitting. And these rules are surprisingly straightforward. I'm going to explain what those first principles physics rules are in this video, and once we've worked through what makes a jet engine tick, I'll show you how to enter your jet engine into PlaneMaker so you can fly it in X-Plane. Before we get started though, there's something y'all have to do to get us on the same page. You need to go watch the YouTube video, Why the Cirrus Jet is So Slow. You have to see that video before you watch this one to understand all the things that go into making a jet engine tick. So if you haven't seen that video, go watch it now and then come right back here. Okay, and we're back. We're all on the same page with how jet engines work. Now let's apply what we've learned in PlaneMaker and then ultimately fly it in X-Plane 12. Let's start off with the subsonic jet engine dynamics in X-Plane 12. What we've got here is thrust curves where we have Mach number on the horizontal axis and thrust on the vertical axis. Each of these lines is an altitude. And so of course at sea level you get the most thrust because you have the most air density, but because your jet engine only has a limited amount of power, and despite what anyone will tell you, I will claim that a jet engine only has a limited amount of power. Because the jet engine only has a limited amount of power, the thrust will degrade as the airplane speeds up. Remember, if you have a limited amount of power available, then the faster you go, the less hard you can push. That is the definition of fixed power. It's less thrust the faster you go. And so we see that here. Less thrust the faster you go is that compressor puts out a constant unchanging horsepower. However, once you get above about Mach 0.5 or Mach 0.6, a ram air effect comes in and that starts kicking your thrust up. And sure enough, in the thrust curves here, the CFM 56 engine, the Boeing 737, you can see the exact same thing that you see in PlaneMaker. You start off with a certain amount of thrust. As you build up speed, the thrust degrades as necessary to hold a constant power output of the engine. And when you get above about Mach 0.5 or Mach 0.6 or so, the ram air effect becomes significant enough that it overcomes that thrust degradation and you start picking thrust up. And so this curve is matched perfectly. And what I love so much about this data is directly derived from the actual jet engine. These curves are derived based on very simple math. The math is simply taking a constant power and running the thrust down as the speed builds and using Bernoulli's law to apply ram air effect to then turbocharge that inlet as it speeds up. The very simple first principles math matches these thrust curves so well. It's absolutely beautiful. Now, you look at these curves coming up and you're like, well, yay, why don't we go faster? As long as these curves are coming up, let's keep making this airplane go faster, man. Don't slow down. Well, here's the problem. They only took these curves up to Mach 0.9. If they were to keep going, they would start to run into the bad news as they approach the speed of sound. Look at this cylinder here. This is a cylinder in supersonic flow, and it has what's called a bow shock around it. The air is piling up and forming this big shock wave. The drag associated with this is absolutely huge. And what do you know? The inlet looks exactly like the cylinder, doesn't it? It's a big, straight, non-swept round shape. As this inlet approaches the speed of sound, bow shocks are going to build up all across that inlet. And something called a normal shock might even eventually form across the face as well. And bow shocks had a huge amount of drag. Normal shocks rob the air of almost all its energy. And so the shock waves will start building up on this inlet as it approaches the speed of sound, and the thrust will absolutely fall apart. They don't show that on this chart because they don't go that fast, because nobody's going to fly a 737 that fast. But But of course, PlaneMaker and X-Plane are all about going to extremes if you have to. And so I actually went on ahead and degraded the ram air effect as we went into all those shock waves. This is all basic first principle stuff. It fits the charts perfectly, and it really makes me enjoy the subsonic jet engine model in this rev of X-Plane 12. Okay, so that's the subsonic thrust, but if you're flying the F4 or the F14, subsonic ain't good enough for you, is it? Let's take a look at the inlet of the F14 and see how this guy manages to exceed Mach 2 without all of these problems that we discovered with the inlet of an airliner. Well, let's take a look at the inlet of this airplane. Notice it's not a big, fat, round shape, but instead it's a razor sharp leading edge. This forms a nice, tight, oblique shock, which has a minimum of drag and does a minimum amount to rob the air of its energy. And the oblique shock coming off of this lip here stays out of the engine inlet. That's why the inlet is swept back. Don't let the shock wave come back into the inlet. And so with this sharp leading edge here, the swept inlet, and then all the control they do for what air is allowed to go when and where at various different Mach numbers, they actually manage to preserve their ram air effect even above the speed of sound. However, there's no magic here. The engine still has a limited amount of dynamic pressure or air pressure that it can withstand. And when you exceed a certain amount of thrust or a certain amount of dynamic pressure, I'm sorry, the show's over. We just can't give you any more. And so we see this here. This is where we've hit a 630 knots equivalent airspeed limit. And what's kind of cool is, while in this case we put 630 knots equivalent airspeed as the maximum dynamic pressure this engine is allowed to deal with, what's kind of cool is the higher you go into thinner air, the higher a Mach number you can get to before you hit that pressure limit. Why? Well, this is a pressure limit in the inlet. The higher you go, the thinner the air gets. And so the thinner the air gets, the faster you can go without hitting the pressure limit. And so isn't this interesting? Each of these curves is at a higher altitude as we get down into lower thrust at a higher altitude. But each of these curves lets you run up to a higher and higher Mach number before you hit your maximum allowable pressure. Isn't that a wonderful thing about flying in thin air? You can go faster before you get to some critical pressure. And that's why these airplanes go faster at higher altitudes. Now, this is really nice and all to hold a nice constant thrust and a nice constant pressure, but at some point, the temperature builds up. Temperature goes with Mach number squared, and so I don't care if you're high, low, or anywhere else, it makes no difference. Once you get to a certain Mach number, you're at a temperature that's going to be elevated, and that temperature, again, elevates with Mach squared. So once you get to, in this case, 120 degrees Celsius of compressed air temperature in the inlet, you gotta back off again to keep from over-temping anything. And so there's your next limit, temperature. And so what we now see is the curves here for the jet engine all come down to pretty straightforward first principles math. The engine has a limited amount of power. As the speed builds up compared to the speed that air is pulled through the engine at a standstill, the thrust degrades to hold a constant power from the compressor. As you speed up, the ram air effect builds. And because this is a supersonic inlet, that ram air is preserved even above the speed of sound, thanks to what must be a sharp inlet and proper management of the airflow coming into the engine. However, there is a limit on the pressure that the engine is allowed to deal with, the indicated airspeed, and you can escape from that by climbing higher to a certain degree. But then eventually you're going to run into a temperature limit. I don't care how high you are, that temperature limit is at some point going to stop you from accelerating anymore. And so this is the thrust curve that results. It's all first principles math, and when you enter these constants in PlaneMaker, you'll be able to set these curves for any engine. So why don't we just take a quick look at a few real engines, just so I can compare my theoretical math with real engines. And so what we have here is the curves for a jet engine, military jet engine, and you can see they just build up, then they hit some sort of a limit, and they level off. And down at sea level, where they can start at 0 speed on the runway, you can even see the speed building up and the thrust degrading. And here's some more curves from some other jet engines, and you can see the same general trend. We build up as we get dynamic pressure and ram air effect build up. Then we hit some sort of a limit where we kind of flatten out, especially at low altitudes here. We flatten out a bit, and that is probably our indicated airspeed limit. And then, no matter how high you go, eventually your temperature is going to be a limiting factor, and your thrust curves are going to start to come down. And so you can see those curves here. So that's how these jet engine thrust curves work in X-Plane 12. Why don't we go into PlaneMaker now and see if we can bring them into practice with an airplane. Okay, so here we are in PlaneMaker in our 737. We'll do the subsonic airplane first and the supersonic airplane, just like we did at the whiteboard. Let's go to engine specs. We'll go to the engines tab. Enter your maximum allowable thrust and afterburner thrust increase. This has been the same since X-Plane 1. I'm not going to spend your time going over that in detail. It's so obvious. Engine location. No, we don't have propellers on a 737. Now we're starting to get good. N2 power curve to drive N1. Remember, hey, look at my video called How Jet Engines Work or whatever at St. Martin's. This is when we went to St. Martin's and got blown around by jet exhaust. I did some decent description of how that N2, which is that tiny little turbine, like in the core, spins really, really fast to drive that big old N1 fan up front. And this is the curve across which the N2 drives the N1. Now let me just talk about this for 1 second. N2 and N1 have no physical connection. N2 is just spinning in the middle of the engine, and the exhaust from N2 runs through a turbine or a windmill, and it's that windmill that drives N1, the big old fan up front. So there is no physical connection between N2 and N1. It's just the exhaust from the core spits out, drives a little windmill that's hooked up to the fan up front, okay? And that little turbine in the middle has to spin like crazy before that big old fan even notices. And because of that, we have this power curve that says N2 power curve to drive N1 is 3.32 for this airliner. And the reason it's such a crazy curve is because that little N2, it better be spinning up to say 55% before that N1 hardly even starts to notice, you know, it just comes up to 12% or something like that. So 3.32 is a decent power curve to enter here. And what this means is that little N2 has to be humming before there's enough exhaust coming out to drive that big old N1 fan. All right, Jet 2, thrust power curve with N1 2.5. I found this to be about right. What this means is that N1 fan really has to be humming before it starts to get any thrust. It's more than a square law. It's halfway between a square law and a cube law. So, in other words, if that N2, or excuse me, that N1, that big old N1 fan is starting at half speed, which is 50% RPM, it's only going to get 6,000 pounds of thrust. 6,000 out of 40,000. So there's that N1 that has to spin up some decent action before you get any thrust. And I think that's just because dynamic pressure goes up with the square of the increase in speed, and power goes up with the cube of the increase in speed. And so we're halfway between the square and the cube here for the thrust. And I say I think because I've looked at what the thrust actually does, and a power curve of 2.5 is what actually matches what the thrust does. All right, now we go to the Jets 3 tab. Of course, that's what I just explained on the whiteboard. And little funny, it seems like these days I only use the whiteboard to magnet up my printouts. I don't actually draw on the whiteboard anymore. It seems like maybe I could save time by just using a wall. But anyway, here we go with our jet engine thrust curves. And look, this is exactly what I showed you on the whiteboard just now. You see your static thrust, it runs down as your speed builds up. Then you get some ram air effect, and then you lose it when you lose all your compression efficiency when shocks start forming on the engine. And you enter your bypass ratio, compressed area, and then you'll notice that if I enter a faster inlet Mach number, like say 0.95, like we might have in a Citation 10 or a fast Gulfstream, for example, the ram air effect is pushed out to a higher Mach number before it starts to fall. Or if I were to go 0.75, well, then at a mere 0.75, you start to lose efficiency in your inlet as as shockwaves start to form. So, I don't know, let's just put in 0.95. That's probably okay, because that's above the speed we're going to operate anyway. And inlet compression is 95%. I found 95, even 100% is just fine. Now, isn't this interesting? My max inlet knots indicated airspeed is all 9s, and my max inlet temp is all 9s. Well, does the CFM56 of this airplane Is it really, infinitely strong? No. The reason I've got all 9s entered here is because we're never going to go fast enough for these numbers to come into play. We're going to have our thrust fall apart above Mach 0.95 just due to shock waves and no more compression efficiency, as we see here. We're not going to get to a high enough speed range of this airplane for max inlet knots equivalent airspeed and inlet max temp to ever really happen. If you want to go dig through an operating handbook and find these numbers, do feel free to enter them, but I think these numbers are out past what we're ever going to encounter in flight, so I wouldn't worry about it too much. Start up and spool up. Idle, we're going to look at the jet section here, okay? Idle N2 for a maximum ITT. All right, remember the way all these turbines work. They're all the same. Turboprops, jets are all the same. There is a combustion in the middle of the engine that is so hot, it will melt the engine if it ever touches the engine wall. Literally, all the time a jet is spent running, there is a temperature in that flame that would melt the engine if it ever touched the engine wall. And the only reason jet engines and turboprop engines, for that matter, are destroyed every single time you fly them, even once, is that there's so much RPM pumping so much air through the system that an insulating wall of air exists between the combustion and the engine wall, and that's literally what protects the engine. So it's beautiful, isn't it? A wall of air between the combustion and the engine wall is what keeps the engine from melting. That wall of air doesn't weigh too much, does it? You don't have to replace it too often, so it's pretty nice. But the drawback is you have to keep a good solid RPM up to build up that insulating wall of air. And if you don't have enough RPM to keep that wall of air built up, your engine's going to melt. So what is that? It looks like for this airplane, for ITT, it's 37%, and EGT it's 34%. I'm sure someone in the YouTube comments is going to say, oh no, we only measure ITT or we only measure EGT. But regardless, it's in basically the 35% ballpark is how fast your N2 has to be spinning to build up enough insulating air to stop the combustion from going out, exceeding your temperatures, and melting the side of the engine. Put another way, get that N2 spinning up to at least 34 or 37% before you introduce fuel, or you will go over temperature because that insulating wall of air is not built up. Auto start engage at 22%. Well, why do we engage at 22% if 37% is the minimum we can ever go? That seems dangerous. Well, the fuel intro start ramps up over 25 seconds. So you're spinning at 22% N2, and it just starts to leak in just a littlest bit of fuel. And then by the time 25 seconds has elapsed and you're up to full fuel flow, you should be well above 37 or 34% N2, and so you should never have a temperature exceedance. And thanks to Dutch Pilot Girl for putting all those engine start videos on YouTube so we can see exactly how the engine starts in these airplanes look. Then your turbine inertia, 1.2 of regular, and a thruster reversal deployment time of 0.8 seconds. All right, SFC, let's take a look at that. Specific fuel consumption. SFC, really simple. SFC is in units per hour. And so what that means is you take your thrust, you multiply it by your SFC, and you have your fuel flow in pounds per hour. Why? Thrust is in pounds, SFC is per hour, multiply the two together, and you get pounds per hour, you see? And that's how you can tell how SFC works. So for an SFC of 0.535, if you have 1,000 pounds of thrust, this would be 535 pounds per hour of fuel flow. And I've got 4 different little targets that you can enter here. We'll start at the bottom and work up. Your takeoff, N1 Mach and SFC, your mid-climb, N1 Mach and SFC, your fast climb, N1 Mach and SFC, and your slow cruise, fast cruise. If I said fast climb, I'd say fast cruise, N1 Mach and SFC, and slow cruise, N1 Mach and SFC. So you just enter the kind of like the edges of the performance envelope, if you will, for the engine, the specific fuel consumption, and the way you find the fuel consumption here is you just say, all right, well, what number do I have to enter if I want to multiply the thrust by this number to get the pounds per hour of fuel flow? So it's super easy to enter this if you know the fuel flow and the thrust of your airplane. And then transmission and radiator, if you've got a radiator in there, you can do your duct expansion and drag and whatnot, and then your sound. Okay, so that's the 7.3. Let's take a look at the new F4, which you may or may not have right now. At the time you watch this video, the new F4 might not have come out, but don't worry, we'll soon. We're getting close. We're getting close to releasing it. This thing is bad. Rodrigo absolutely outdid himself with this F4. And this is all tuned by Huss, who's the Israeli Air Force F4 instructor pilot. So we really got this F4 just like the real plane. So let's do our supersonic dynamics. Yeehaw. I'm going to bypass everything except Jet 3 because everything is the same except for the Jet 3 tab. So what do we got? No bypass ratio. Everything goes right through the middle. Compressor area 8.05. Inlet Mach is 2.6. Because we entered an inlet Mach number that is greater than 1, that's how we telegraph to X-plane that we've got a supersonic inlet with all the sharp edges and swept inlets and, inlet control, air, boundary layer control management, all that stuff to get supersonic air into the engine efficiently, and the thrust won't just fall off at Mach 1. So entering an inlet max Mach number above 2.6 is what telegraphs we got a supersonic inlet with all the concomitant curves that we're about to go over. Inlet compression efficiency, I've entered 1 because I've found surprisingly that works pretty dang well. Inlet max knots equivalent airspeed. Think of this as just a number that shows up in your airspeed indicator. So when you're above 630 knots indicated, you don't get to do much more and your thrust kind of falls off. But if you want to go faster, you can always go higher. And so if you go up to, say, the 25,000 foot curve here, you can go all the way up to Mach 1.5 before you hit 630 knots indicated airspeed. And so you can delay that pressure limit on your engine until you get to a higher Mach number if you go higher. If we go up to, say, 50,000 feet, we can all go all the way up just over Mach 2 before we hit our 630 knots equivalent airspeed. So the higher you go, the faster you go, because you're not hitting that pressure limit on the engine until you get to a higher speed. Isn't that cool? And so now we know why these jets will do Mach 2 up high, but only just over Mach 1 down low. You got to have that engine pressure limit honored. The higher you go, the faster you go without hitting that pressure limit of a maximum indicated airspeed. However, there's no getting around the fact you've got a max allowable temperature. That temperature goes up as the air compression happens as a function of Mach number. I don't care what altitude you're at. And so this airspeed limit here, if we didn't have that limit, if we made the engines out of, unobtainium or whatever, look, you get a little more juice out of them. And if you had to make them out of Play-Doh or something, well, then they would look like that. But with aluminum, or we can see up to 120C, I guess, you can get a curve that looks like this. And what's kind of nice is you can get some decent speed out of the airplane. What is kind of disappointing is, I don't care how high you go, you've got this temperature limit up here that you just can't exceed. And if you could maybe endure more pressure, you get the curve to look like that. And if you couldn't endure so much pressure, well, then the curve would look a little more like this. You see? Isn't that cool? So you can just say, hey, how strong is the material I'm building this engine out of? How much, knots equivalent airspeed can it withstand? Maybe it can do more. And how temperature resistant is the material this engine made out of? And you can run up that temperature if you got a more temperature resistant material on the airplane. And by doing that, you can see what these engines can do when they're made out of real world materials. Isn't that cool? And when you play with this curve a little bit, you see that engine designers would really love to have a material that's really strong and doesn't get weak when it gets hot. That is the holy grail, I guess, for jet engine design. And playing with this really lets you see that. So anyway, that's how you enter this stuff into X-Plane. And I will let you take these airplanes flying yourself, because you don't need me to show you how to do that. You can do that on your own. Oh, who am I kidding? There's no way we weren't going to go flying. Yeehaw! Oh my gosh, it doesn't matter what you do with the brakes in this airplane on an icy runway. Brakes don't matter. Yeah.